Hello everyone and welcome back to the channel. Today we're going to be looking at solving exponential equations. In our discussion we're going to be looking at solving different types of exponential equations, what I like to refer to as type 1 equations, type 2 equations, and also dealing with other problems that will involve exponents as well. When it comes to solving exponential equations and solving many other types of equations in general, there's always an underlying property involved in the process of solving the equations. In this case, we're going to use the following property. If a to the x power equals a to the y power, then x is equal to y. If the bases are the same, then the exponents are going to be equal to each other. This particular property will come into play when we're solving type 1 exponential equations. What exactly are type 1 equations? Well, these are equations that involve a common base. And so the objective here is to use the properties of exponents to express each side of the equation in terms of the same base. We apply the property and then after we apply the property, we solve the resulting equation. So let's get into some examples. For our first example, we have 5 to the x power equals 125. In this problem, one thing that we observe is that 125 is a power of 5. So we can express the right side, 125, as a power of 5, in this case 5 to the third power. Our equation then is 5 to the x power equals 5 to the third power. Now that we have both sides expressed in terms of the same base, we simply set the exponents equal to each other, which gives us our solution of x equals 3. Let's get into something that's a little bit more challenging. So for our second example, we have 6 raised to the power of 4x equals 36 raised to the power of 9 minus x. So once again, we want to express both sides in terms of a common base. We can see that on the right side, 36, the base, can be expressed as a power of the base on the left side, which is 6. So 36, that's 6 squared raised to the 9 minus x power. Now on the right side, we should also do some simplification. We can apply the power property of exponents. We multiply the 2 by the 9 minus x, and that gives us 6 to the 18 minus 2x power. Now you want to make sure that you do that part before we set the exponents equal to each other. We can apply the property, set the exponents equal to each other. 4x equals 18 minus 2x, and then solve the resulting equation. Add 2x to both sides to get 6x equals 18, and then divide both sides by 6 to get our solution of x equals 3. Let's kick it up another notch. Here we have the equation 27 to the x minus 3 power equals 9 to the 2x plus 1. Now, once again, we want to express both sides in terms of a common base. Now, here, there's a bit of a challenge because 27 cannot be expressed as an integer power of 9. However, 27 and 9 both have a common base. They're both powers of 3. So we can express both of these in terms of the base of 3. 27 is 3 to the third power. 9 is 3 to the second power. Once we express those numbers as powers of 3, we can simplify these expressions by multiplying the exponents. The left side would give us 3 to the 3x minus 9 power. On the right side, we have 3 raised to the 4x plus 2 power. Now that we have the same base, we can now set the exponents equal to each other and solve the resulting equation. Our equation then becomes 3x minus 9 equals 4x plus 2. Subtracting 3x from both sides gives us negative 9 equals x plus 2. And then finally subtracting 2 from both sides to get a solution of x equals negative 11. Now let's move on to type 2 equations. These are equations where we cannot find a common base within the equation. So the general method for solving these problems will be to apply logarithms to both sides of the equation. And usually we'll do natural logarithms, but any base will work. Then we can apply the power property for logarithms, which we'll review briefly, and then solve the resulting equation. Simple example of this would be the equation 5 to the x power equals 79. So the first thing we want to do here is to take the natural log of both sides of the equation. That gives us the natural log of 5 to the x power equals the natural log of 79. The next step will then be to use the power property of logarithms. And if you recall the power property of logarithms, if we have the log base b of m to the p power, that's equal to p times the log base b of m. We essentially take the exponent, bring it out in front, and make it a coefficient. When we apply the property here, that will give us x times the natural log of 5 equals natural log of 79. Solving the resulting equation, all we need to do here is divide both sides by the natural log of 5, and we have our solution, x equals natural log of 79 over natural log of 5. Now this we would regard as our exact solution to the equation. We could, of course, plug this into the calculator to come up with an approximate solution. Most of the time when you're doing problems of this type, it is required that we express the solution in exact form the way that we have it here. Let's take a look at our next example. Here we have 3,000 times 1.032 raised to the 12t power equals 10,000. So we'll follow through with the same steps. At a particular point, we will want to take the natural log of both sides. First, however, you want to isolate the exponential expression first. In this problem, the exponential expression is 1.032 raised to the 12t power. In order to isolate that, we'll need to divide both sides of the equation by 3,000. This leaves us with the equation 1.032 to the 12t power equals 10/3. Now that the exponential expression is isolated, we now take the natural log of both sides. So we have natural log of 1.032 to the 12t power equals natural log of 10/3. Our next step would then be to use the power property. So the exponent 12t, bring that out in front to make that a coefficient. So we have 12t times the natural log of 1.032 equals the natural log of 10/3. So all that remains to get t by itself. Oh, that's a mistake. So after we bring the 12t in front, we have 12t times the natural log of 1.032 equals the natural log of 10/3. And all that remains for us to do now to isolate the variable t is to divide both sides by 12 times the natural log of 1.032. So our solution is t equals natural log 10/3 over 12 times the natural log of 1.032. And once again, this is the exact form of the solution. So you can leave it like this. To approximate it, just plug everything in the calculator. For our next example, we have probably one of the more challenging exponential equations. Here we have 4 to the 2x minus 1 power equals 9 to the x minus 4. And the challenging part to this one usually lies in the algebraic steps that are required to get to the solution. Now, we still go about the same process. We're going to take the natural log of both sides of the equation. Here, we don't have to worry about isolating exponential parts because on each side, we have just one exponential equation. So we begin by taking the natural log of both sides. We have natural log of 4 to the 2x minus 1 power equals the natural log of 9 to the x minus 4 power. Then we apply the power property, and so here we'll apply it to both sides of the equation. So we take the entire exponent in front of the logarithm. That gives us 2x minus 1 times the natural log of 4 equals x minus 4 times the natural log of 9. Now at this point, we're trying to get x by itself. We have it on both sides of the equation. One way that we can solve this is by distributing the natural log across the algebraic expressions on both sides. On the left side, that gives us 2x times the natural log of 4 minus 1 times the natural log of 4, which is just natural log of 4, equals x times natural log of 9 minus 4 times the natural log of 9. This does look a bit messy. Our goal is to get x by itself. We're going to take the terms that contain x and get those on the left side. We're going to subtract x natural log of 9 from both sides of the equation. And then also, that'll bring all the x terms to the left side. Then we'll add natural log of 4 to both sides of the equation. Our equation then becomes 2x times the natural log of 4 minus x times the natural log of 9 equal natural log of 4 minus 4 times the natural log of 9. On the left side, we have all the x terms, so we can factor out the x to get x times 2 natural log of 4 minus natural log of 9 equals natural log of 4 minus 4 times the natural log of 9. So all that remains for us to do now is divide by 2 natural log of 4 minus natural log of 9 on both sides for our final solution of x equals natural log of 4 minus 4 natural log of 9 over 2 times natural log of 4 minus natural log of 9. If you plug this into the calculator, be sure to include parentheses for the numerator and the denominator so the calculator isn't confused about the operations. All right, so now let's look at a challenging problem with exponential equations. Here we have 64 to the x power minus 8 to the x plus 1 power equals 33. Now what's challenging about this one is that we have not only different bases, but also we have this additional term 33 that's not an exponential expression. So this one has a little bit of a trick to it. So let's break this down. First of all, if we look at the bases, 64 and 8, we can express 64 as a power of 8, namely 8 squared. So we can write this expression as 8 squared to the x power. 8 squared to the x power, we can rewrite that as 8 to the x power squared. All right, so all we're doing here, since we have a power raised to a power, we can switch those powers and still get the same result. Moreover, the middle term, 8 to the x plus 1 power, is simply 8 to the x power times 8 to the first power, or just 8. So the second term we can express as 8 times 8 to the x power. Now, you might not recognize this, but the equation as we have it written is actually an equation that's quadratic in form. We can make a substitution to show that out. So let's say we let u equal 8 to the x power. Our equation would be u squared minus 8u equals 33. Now we can clearly see that this is a quadratic equation, and we can solve it as a quadratic equation. Bring all the terms over to one side, so we'll subtract 33 from both sides. That gives us u squared minus 8u minus 33 equals 0. And this particular quadratic expression is factorable. This gives us u minus 11 times u plus 3 equals 0. Setting each factor equal to 0, u minus 11 equals 0, and u plus 3 equals 0. We have two solutions, u equals 11 and u equals negative 3. We're not solving for u, we're trying to solve for x. So we'll need to back substitute, which will make our equations 8 to the x power equals 11 and 8 to the x power equals negative 3. In the case of the second equation, 8 to the x power, no power of 8 is going to yield a negative number. No real power of 8 is going to yield a negative number. So there's no solution for the second equation. The first equation, we can solve that. Much like a previous example, we take the natural log of both sides, then apply the power property, give us x times the natural log of 8 equals the natural log of 11, and then divide both sides by natural log of 8, which gives us a solution of x equals natural log of 11 divided by the natural log of 8. So when you're working on some of your homework problems, sometimes you run across some of these examples that you can actually convert into a quadratic equation. So you do the conversion, solve it as a quadratic equation, but remember to back substitute it into the original variable to solve for that variable. All right, so that will wrap things up for this video. I hope that this was helpful. If you have any questions, please put those questions in the comment section. If you enjoyed this, please consider liking and subscribing to the channel. And if there's any other topic or any other problem that you would like me to go over, just drop that in the comment section as well. Thank you very much.